This is Austin Keating with the Remediation Technology webinar. With me today is Brian Pincard. He's the co-founder and CTO of Aquagga. He's here today to talk about the new MCLs for PFAS and just hoping to pick his brain on that and the options he offers to the industry. So thank you for joining me today, Brian.
Thanks, Austin. It's nice to be here.
So yeah, could you just give me a brief overview of what Aquagga does and what you think about the news?
Happy to. So a little background about Aquagga. We are a startup company that formed in 2019, and our sole focus, our sole mission is to bring new technologies to the market centered around PFAS. When we started the company, what we learned really quickly, what we heard from the industry is that PFAS treatment, especially PFAS destruction, was this huge market need, emerging market need. And the technologies really didn't exist, especially in the PFAS destruction realm, for dealing with these contaminants. So we are working with the technology called hydrothermal alkaline treatment. It's a technology that was first developed at the Colorado School of Mines. It's also known as HALT. That's the short version of it. And basically, we've been working to get the technology from the lab scale to the commercial scale so that we can offer it out to the industry. Put another tool in the toolbox of folks working on drinking water treatment, solid waste management, environmental remediation, and all of these other challenges around PFAS. So Austin, as you mentioned, the EPA recently proposed some new drinking water MCLs, that stands for maximum contaminant limits, centered around PFAS. And there were 6 PFAS that were identified: PFOS, PFOA, PFNA, PFHXS, PFBS, and GenX. And the unique thing that they did is they set limits for PFOS and PFOA, each at 4 parts per trillion, very, very low. And then for the other 4 compounds, they propose what they call a health index. So each compound has an individual number and in terms of parts per trillion. And then you kind of use a weighted average of the total of the 4 compounds to get that health index. So again, this is still a proposed MCL. There's a public comment period that's open right now. I believe the EPA is also hosting some webinars around the topic. And from my understanding, the rulemaking process, I think these regulations, once they're formally in place, would start to be enforced in about 3 years. So the good news is, this is a step in the right direction. The EPA is moving down the path that they set out in their PFAS action plan. So, things are moving forward. Of course, these processes take time. That's just a consequence of the rulemaking framework that's been put in place for drinking water contaminants. But for us in the destruction space, we're excited to know that in the future, there's also going to be guidance coming out around discharge regulations, as well as site sampling activities at the federal level. So we're watching this very closely. Again, it's a step in the right direction. It is motivating a lot of folks to start taking action to deal with PFAS, to start sampling for PFAS. And in general, it all just spurs along more activity to help get these contaminants out of the drinking water and out of the environment.
Can I ask if HALT is commercially viable yet?
So to speak a little bit towards where the technology is, it's always a process getting a technology like this to the commercial scale. We're building real hardware, real equipment. It takes real dollars to do that. And we're dealing with kind of a complex technology. We use high pressure, high temperature water. We operate at a high pH, and under these conditions, we're able to facilitate PFAS destruction. So as you can imagine, this isn't something that we can build for $100 and ship out to the industry. This takes real dollars to get it there. And where we have the technology today, we've built a system. It's a standalone unit that we have in our facilities here in Tacoma, Washington. It's about the size of 2 home refrigerators, and we use it for performing bench tests or feasibility tests for clients. So basically, we'll get a sample from the client, anywhere from 3 to 5 gallons of really contaminated PFAS-rich wastes. We'll process it, show that we can destroy the PFAS, and send it back to the client. So what's really exciting is we've now done a few of these projects. we've been able to show we're able to destroy all PFAS compounds that we've tested, and B, we're able to convert all of those PFAS compounds over into non-toxic, benign salts. So the gold standard with PFAS destruction, you gotta remember PFAS is a fluorocarbon chemical. So how do you break all those carbon-fluorine bonds? The gold standard is to break all of the carbon-fluorine bonds. And if you do that, you should measure the same amount of fluoride in your final product as you have in the form of fluorine in your initial PFAS. So we've been able to demonstrate that now in our system here, which is very exciting. Shows that HALT is not only commercially viable, but it doesn't produce any harmful byproducts. It's safe, it's effective, and we have 2 commercial scale systems that are currently being fabricated on the way. Should be up and running at some point in 2023.
Well, you'll be well ahead of the MCLs actually going into production, I suppose.
Right.
So one of the things I was going to ask you about is, does your product help to address this need of the limited availability of PFAS disposal? I was in New Orleans recently, and I just happened to be by this hazardous waste disposal. Well, it's a disposal facility, but they only do hazardous waste every once a month or once every couple months or something. And there's this huge line of trucks, and it's a very in-demand service already. So one wonders how it's going to be 3 years from now, like you said.
Yeah, it's absolutely fascinating to see how fast the market is shifting and how fast the market's getting more sophisticated around PFAS. I mean, 10 years ago, if you found PFAS in your drinking water system and you wanted to do something about it, A, 10 years ago, there was nobody required to do anything about it, but B, the approach was using activated carbon filtration system. When the carbon is spent, when it's loaded up with PFAS, send it off to the incinerator and you're done. That's it. Today, the DoD has now enacted a moratorium on incinerating any PFAS-laden wastes coming from their sites. A lot of commercial landfills are no longer accepting PFAS-impacted waste. A lot of local municipalities have banned incineration of PFAS. The options are becoming more and more limited for waste disposal. And what's interesting, if we go back to the conversation around the MCLs and about drinking water, most drinking water utilities, they want to pay for a solution and have the problem solved. They don't want to have to think about putting a full treatment train together and what are we doing to manage our residual byproducts of drinking water treatment. They want to pay for a service that comes and takes the waste and deals with it. So what we're seeing is there's a lot of interest in the solid waste management side of the house in these destructive technologies. These are the folks that are going to be taking the spent filter materials, spent filter media away from the drinking water sites to their facilities, and they're ultimately going to be responsible for the PFAS that come with it. So there's a lot of interest in treating landfill leachates. And then what do you do with the treatment byproducts from the landfill leachate? Again, you need a destructive technology at some point in that treatment chain, in that value chain. So yeah, it's as I mentioned, it's really interesting to watch the market get more sophisticated around these technologies and kind of figuring out what the best approaches are for each of these different problems.
Could you maybe emphasize why HALT has a lot of potential for the secondary wastewater products?
It gets into a lot of nuance, but a lot of it has to do with what the specific characteristics are of these secondary wastes and what the customer desires, right? So there's a few PFAS destruction technologies out there which have reached some level of maturity, have gotten out of the lab. HALT is one of them. Supercritical water oxidation is another that's getting a lot of attention. Electrochemical oxidation. And there's a couple others that are kind of trailing along, and again, really it comes down to the specific nuance. So for example, electrochemical oxidation can work really well to break down PFOS and PFOA, but really struggles with a lot of the short chain PFAS compounds. And when we look at the regulations, PFBS is now on the list. That's a short chain PFAS. There's some customers that have even shorter PFAS compounds, which may or may not be regulated, but they're still open to liability if they're discharging those compounds. Supercritical water oxidation and HALT are the only two destructive technologies that can destroy all PFAS compounds, period. And there's really pros and cons with each one. So SQO is really good with energetic feedstocks if you have high levels of total organic carbon present, like if you're treating sewage sludge that's impacted with PFAS, like that's a good application of SQO. You have about 10% organic content. SQO can actually take advantage of the organic content to heat the process, drive the process. It's an energetically favorable feedstock. However, on the flip side, SQO is really hard to apply to salty liquids. And some of these primary wastewater treatment technologies produce a really salty effluent. And that's where HALT really shines. HALT can really deal with the salty wastes quite well, doesn't have the same challenges as supercritical water oxidation. But on the flip side, HALT doesn't have that benefit of treating energetic wastes. So again, it's like certain feedstocks align better with different technologies. To give you a specific example, there's a technology using regenerable ion exchange resins to do wastewater treatment. So you have these ion exchange resin adsorbents. They can capture PFAS, and then you can use a solvent rinse to strip the PFAS off the resins, distill the solvent mixture, and you're left with this really salty PFAS-rich brine. You know, we're talking 2% sodium chloride by mass. And we've demonstrated that HALT can be used to treat that, treat all the PFAS, doesn't have any issues with the salts. Really good application there. Another good example, foam fractionation is a separation technology that's really gaining a lot of market traction. It produced a PFAS-rich liquid, sometimes containing, you know, high levels of salts or other co-contaminants, depending on the primary wastewater source. And again, pros and cons with using some of these different technologies, but we've shown that HALT can treat the PFAS, can do it in an energetically favorable manner, and doesn't have some of these processing challenges that other technologies do. So we're very confident it can be applied for a lot of these impactful use cases.
Is there anything else you want to share about HALT, where you see the industry going in the future? Like you mentioned, the products are being fabricated now and will be ready this year. Anything else you want to mention?
The other thing I'll mention is just, you know, HALT is a nice technology. It's a bit simpler than some of the other technologies. So that what that translates to is just cheaper CapEx and lower operating requirements. So we think that makes it an attractive option for customers that have some PFAS destruction needs and aren't necessarily wanting to purchase like massive, expensive systems.
I appreciate your time, Brian. Thanks for joining us.
Yeah, of course. It's my pleasure, Austin.
Our second segment today is with Maureen Dooley, Vice President of the Industrial Sector at Regenesis. She's here to talk today about her recent story on remediationtechnology.com, covering remediating aqueous film forming foam, or AFF, release sites at airports, particularly with in-situ colloidal activated carbon. So welcome, Maureen.
Well, thank you, Austin. I appreciate it.
So first off, could you explain what in-situ colloidal activated carbon is and how it can be used to remove PFAS from groundwater?
So when you think about airports, they've been required to have and to test AFFF. And so the AFFF has been on property. And as a result of all of this testing, the PFAS compounds that are associated or make up the AFFF make their way into soil and groundwater. So it's well established that PFAS compounds will sorb to activated carbon. So what Regenesis has done is we've developed a formulation of activated carbon that is made up of very small particles, carbon particles that are 1 to 2 micron in size, and they're suspended to create this colloid. So this colloidal formulation is injected directly into the subsurface, and the activated carbon particles themselves will become adhered or really part of the soil matrix. So this colloidal activated carbon can be injected, as we said, in the subsurface. And really what we're trying to do is create a Brita filter. Um, and let me finish that. So what we're trying to create is this Brita filter that's used to sorb contaminants, and in this case, specifically PFAS compounds.
I should mention your story shares key takeaways from a study published in the Remediation Journal, authored by Dr. Grant Carey, an expert in groundwater modeling and president of Pour Water Solutions. He and his co-authors evaluated in situ colloidal activated carbon, for short, we can say CAC from here on out,
Yeah.
and its impact on PFAS at sites where AFFF has been used heavily. So what were their findings?
The work that was done by Dr. Grant Carey and his group was really quite exceptional. They ran a study where they were evaluating a lot of work that Ben had conducted at these airport sites. And really, one of the biggest takeaways is that some of these most prevalent PFAS compounds, the ones that are of concern that are associated with, the AFFF, are quite readily adhered to or sorbed by the activated carbon, which makes this a remedy or an approach that can be very effective for these contaminants that are most prevalent at the airport sites.
So Regenesis offers Plume Stop as an effective material to remedy PFAS from groundwater. But as I understand it, the technology is still somewhat new. It's uncertain how long these remedies will remain effective. Do you have any findings to share about the longevity of CAC?
Yes, and honestly, that is really one of the big questions. And getting back to Dr. Carey and the paper that he presented and that we wrote about, he spent a fair amount of time talking about, looking at modeling and longevity, because that's what's really, critical. If you're going to create this in-ground Brita filter, well, how long is it really going to last? Now, what's interesting, many of us, may be familiar with, GAC systems and this breakthrough. So, well, why is this different? Well, there are a couple of reasons. When we're working in the groundwater environment, the velocities are just so much slower than what would happen or what would occur during, the flow through a GAC system. So with these slower velocities, we have so much longer longevity. The second point is that the very small particle sizes have a lot of surface area, and that creates a the kinetics or more rapid kinetics or more rapid sorption kinetics, I should really say here. And so because of that, we have slower flow, better kinetics, and it translates really to looking at, decades of longevity. And that's really one of the big points that came out of Dr. Carey's paper as well.
Could you help explain why CAC is good for the dominant PFAS contaminants at airport sites, namely PFOS and PFHXS? I think I'm saying that right.
Certainly, absolutely. Yeah, those two compounds, dominate the PFAS compounds that are detected at the airports. And, due to this hydrophobicity of the sulfonate group, these perfluorosulfonates are really particularly have very good sorption characteristics to the carbon. So again, key compounds, they sorb really well, and they're the key compounds that we find at airports or part of AFFF. And so this is really a good technology fit for those compounds.
As I understand it, you can also use granular activated carbon to remediate PFAS from water. How does CAC compare to ex situ P&T systems that use granular activated carbon?
Yeah, the pump and treat systems are, quite common. People are familiar with those. And but there are some really key differences. I think one of the biggest ones is when you use in situ application, an in situ application of the colloidal activated carbon, there's no O&M. You apply it and that's that. And there's no waste produced. So when you have a pump and treat system, what do you do with this waste? So there's a transfer. And a lot of landfills aren't taking, where do you put it? Nobody's taking this. So that's a real concern. The in-situ approach is also very sustainable. I mean, we're not running pumps, we're not running systems, we aren't, we aren't putting, greenhouse gases, these emissions into the environment, so it's particularly sustainable. And when we're talking about airports or industrial properties, these are complicated sites and there's a lot going on, these airplanes landing on runways and things like that. So infrastructure is important and very, very sensitive, and the operations at these facilities. So by taking an approach, an in situ approach, there's very minimal disturbance, there's nothing left behind. So there's an easy integration into the programs and into these properties, again, with this minimal disturbance. The cost, typically, we're about 10 times less than pump and treat, and you can also get really immediate results.
Since you wrote this piece, I'm curious if you want to weigh in on the news that's happened since you wrote it. The Biden administration proposing regulations targeting 6 PFAS compounds in drinking water. How does Regenesis's work play into this fast developing market?
No, that's a question. I think really for me, I say this is when things get real, honestly. Um, we've all been wondering, where was this going to land? Were there going to be standards? What are the standards? I think a lot of people, facilities, organizations have been waiting for this, and so now we know. So we know what's in front of us. So, where does Regenesis? We stand to assist people. We've that are confronted with this really important issue and problem. It's not simple, but we have a cost-effective, sustainable solution, and we've been doing this. So we've had over 30 applications, and so over this time period, we've learned a lot. Well, while the concept of sorbing the material, and our purpose here really is, we sorb the PFAS contaminants, we get it out of the groundwater, so we're removing this exposure and removing this risk. But where it gets complicated is how we apply it, to apply it effectively so we can meet these low targets and sustain it. So our experience, over the last, many, I'd say 6, 7 years of doing these PFAS specific applications have been really helpful. So again, I think we're ready to, be able to help people and provide assistance.
So, is there anything else you want to share about the effectiveness of colloidal activated carbon, particularly from the biodegradation perspective?
That's an interesting question. When you talk about biodegradation, the answer is in a couple of different ways. So the colloidal activated carbon itself, that stays. What we're doing is that's going to become part of the soil, and we're changing the FOC. But let's talk about the contaminants themselves. So PFAS compounds are not subject to degradation or any chemical reductions, at least yet. So that's why it's critical for trying to get to these parts per trillion levels that we get this really good distribution. We're able to take it out of groundwater. Now we certainly remain hopeful that at some point something comes along that can break these compounds down. When working with other compounds like chlorinated solvents, petroleum hydrocarbons, which may be, say, part of the groundwater mixture of contaminants that also include PFAS compounds. The surface of the colloidal activated carbon is really great for microbial growth. So you can have this film of bacteria ready to biodegrade some of these other contaminants that may be mixed with the PFAS compounds.
That's really interesting, the dual purpose aspect of it. So, this is a very interesting technology. I appreciate you sharing your insights about the article you wrote and diving a little deeper into it. So, appreciate your time, Maureen.
Awesome. We appreciate your time as well, and thank you very much.
Thank you.